Today, we are starting into projectile motion. This takes everything that we've learned so far and combines it. Get excited. Okay. So, first thing, learning objectives. Just today, at the end of the lesson, you'll be able to describe the motion of something in projectile motion, moving both horizontally and vertically, and why it moves that way, and calculate its position, displacement, velocity for both the horizontal and vertical directions for an object in projectile motion. Okay, so quick review. I want you to explain why or how, describe the motion of this ball after it leaves my hand before I catch it. This whole process in detail, why it does that, specifics about all that stuff. Tell your neighbor. Have a discussion.
Oh my gosh. I just bought it and he's trying to get stagnant.
So when you do we have a study hall? Do you have a study hall?
I have a virtual test period.
You want to do the test then?
Yeah.
Okay. Okay. Hopefully in that conversation you said something in regards of experiences of constant acceleration of 9.8 meters per second squared in the negative direction. It slows down as it goes up. It speeds up as it goes down. The highest point velocity is 0. Do that. Okay. And why does it move that way? It's because the force of gravity is acting, always pulling it straight down. Okay. All right. So have this hoop on this vase. Okay. Now, the object we're focusing on is the marker. How do you describe the state of motion of this marker? How is it moving? It's not. Okay, it's at rest. Good with that? So, it's going to remain at rest until something crazy happens. So, ready. 3, 2, 1. Boom. Boom. Yeah, that was awesome. That was cool. You guys see that? On the camera, you see that right there. That would have been less than ideal. All right, so did the marker remain at rest? No. Why not? Gravity pulled it straight down, right? That's not the amazing part. Okay, we knew that was going to happen. What happened to the motion horizontally? It horizontally, did it move anywhere? No. That's why I was able to fall into this. Okay? It did what inertia wanted it to do in the horizontal direction. Not in the vertical. Vertical's like, ah! But horizontally, it's like, dude, I'm at rest. I want to stay at rest. Because what forces we're acting on in the horizontal direction? None. You good with that? Okay. So, a really important paradigm, a way to think for this unit, for this projectile motion stuff, is to separate the motion and the forces, what's going on in the horizontal direction and what's going on in the vertical direction. Okay. Oops. Let me change this. On the marker. Nope. There we are. So, forces acting on in the vertical direction, force of gravity. Okay. And it was in free fall. Good with that? Okay. Because of force of gravity. What forces are acting on the mark in the horizontal direction? There were no forces. Horizontally, it remained at rest because that's what inertia wanted to do. In horizontal direction. You okay with that? Now, moving to a little more involved things. Okay, a projectile is when something is in free fall but moving horizontally. When something is moving horizontally while in free fall. Okay. So, projectile motion is something moving when something is moving horizontally while in free fall. This would be an example of projectile motion. So after it leaves my hand and before I catch it, what forces are acting on the ball? Tell your neighbor. After it leaves my hand, before I catch it. What forces are acting on the ball while it's in projectile motion? Correct answer is just gravity. Get with that? Inertia is playing a part, but that's not a force. That's just what the ball wants to do naturally. Okay? So just the force of gravity going straight down. Okay? All right. So, actually, let's flip that too while we're at it. So, all right. So, what forces are acting on a projectile in the vertical direction? Force of gravity. Okay. And how is something moving vertically? It experiences. Ooh, brain fart there. Let's try that again. It experiences constant acceleration of gravity in the vertical direction because of the force of gravity. I'll write that out. It experiences a constant acceleration of gravity, negative 9.8 meters per second squared in the vertical direction because of the force of gravity. Okay? That's not crazy for us. Here's the part. What forces are acting on in the horizontal direction? Okay, there are no forces. Okay, so if something's moving, what does it want to do? Continue moving. So it continues moving at a constant velocity in the horizontal direction because because that's what inertia wants to do. Continues moving in the horizontal direction because that's what inertia wants to do because there are no forces acting on in the horizontal direction. Good with that? Okay, this next slide, I ask a question, but I'm really just going to tell you the answer. I'm just going to make a statement. The statement is both motion and forces in the horizontal direction are independent of forces and motion in the vertical direction. Motion and forces in the vertical direction are independent of forces and motion in the horizontal direction as well. Okay. The forces and motion in the horizontal direction do not affect at all, are independent of motion and forces going on in the vertical direction. They cannot affect each other. They're completely independent of each other. And this is one of the paradigms, the perspectives that you need to be able to be successful at projectile motion, is to separate out, hey, how is this thing moving horizontally? What forces are acting on horizontally? Hey, how is this thing moving vertically? What forces are acting on vertically? And know that those two answers to those questions don't influence each other. They're independent. They don't affect each other. Okay? And that's why the marker was able to fall in the vase, because the force of gravity was vertical, did not affect the horizontal motion, so it remained at rest. Good with that? Okay. Good. Check that question out. Everybody have a guess? Understand the scenario? Throwing it horizontally, same height, we're dropping it. Which one's going to hit the ground first? Kylie, rotate your desk that way. That'll work. Nope, you're good. Should be good. Hopefully good. We'll find out. That'll be close. Won't be catastrophic though. All right, so this little device drops this one and shoots this one. Okay. Two disclaimers. Number one, this is very anticlimactic. It's more of like a bumps it out, not really like shoots it out. It's just kind of like, okay, whatever. Secondly, you're probably not going to see it. So you're just going to listen. Okay. So this one's made of plastic. This one's made of steel. Okay. So ready? Everybody got a vote? Hypothesis. Which one's going to hit the ground first? Then 3, 2, 1. What'd you hear? Same time. Crazy. Now, you might have been able to guess that just because, well, it's physics class. Thank you. And, crazy things like that happen. He was just trying to trick me, and I didn't fall for it. I knew. It didn't make sense to me, but I knew it's got to be the same. It's physics. So let's figure out why. So, follow-up question. Thank you. Thumbs up if you have a guess. Have a conversation. Correct answer is C. C. I threw one of them. One was definitely not starting at rest. How can you say C? I mean, everybody said it. I heard it. C, C, yeah, C. Why C? Yeah, Andrew. Yeah.
Because it's asking for vertical direction.
So this is the important part. It's just asking for the vertical direction. Okay. It was moving initially. Absolutely. It was going, I don't care how fast it was going, it was going. Okay. But it was moving horizontally. How fast was it going up or down initially? Initially, it wasn't. Just moving horizontally. So both of them started at rest vertically. Both of them experienced the same acceleration of gravity in the vertical direction. Both fell the same distance vertically. Therefore, both of them will hit the ground at the same time. You okay with that? Okay. From the vertical point of view, their motions were identical. Talk to your neighbor. Correct answer is C. From the vertical point of view, their motions were identical. Okay, they both started from rest. They fell the same distance. They fell for the same amount of time. They both experienced acceleration of gravity. Their Indian velocities are going to be identical. Okay, one way to pretend, like, look at this is pretend you didn't have depth perception. Okay, and the one that was shot or thrown is thrown straight at you. The one that was dropped is right here. Okay, and so what it looks like is this. Okay, you can't see it coming at you. It just looks like it's dropping. Okay, the horizontal motion is independent of how it's moving vertically. You okay with that? Thumbs up when you have a guess. Have a conversation. Tell them why. Okay, correct answer is A. Okay. This is the same exact question. We're using the same rationale to answer this question as which ball is going to hit the ground first if I drop them from rest. Same time? No, it's whatever started closer. Okay. The only difference is I threw this one horizontally, but vertically it's still at rest. Good with that? Okay. Tell your neighbor. Correct answer is, what do you think? Correct answer is A. Okay. Why? Because the motion, the horizontal motion, is independent of the vertical motion. There are no forces acting on in the vertical direction. No, sorry. There are no forces acting on in the horizontal direction, just vertical. It's doing exactly what inertia wants to do, and that is maintain this whatever velocity it has right here the whole time until it hits the water, and then game over. But that's not projectile motion. Okay. While it's in the air, it's maintaining that constant velocity. Good with that? Okay. So if we were able to look at this car in a strobe light, here's what we would see. So these vectors are not forces; they're velocity. Okay. So you have this initial velocity going off the cliff or a ball off of a launcher or something. Okay. Horizontally, it maintains that velocity the whole time. Does not change. It's constant. Okay. So as the ball falls, it still has this velocity that's constant because there are no forces acting on it. But vertically, initially the vertical velocity is 0. Little subscript Y is for the vertical, like x-axis, y-axis. You okay with that? Initial vertical velocity is 0, but over time, vertically, it speeds up. That makes sense? Experiences acceleration. And that's exactly, this is something dropped. This is exactly what happens with something that goes off horizontally, is it speeds up in the vertical direction as well. So it is moving both horizontally and vertically at the same time. Now, if the ball or the car had a speedometer that was registering how fast it was going as it's going through the air, it wouldn't read the black arrow. It wouldn't read the green arrow. What it would read would be the resultant velocity of the green and the black. Okay? It would read that speed. That speed. Okay? So, just making this up, let's say this was 3 meters a second, 4 meters a second. The ball would be moving at 5 meters a second in that direction at that moment in time. 3, 4, 5 triangle. Just making that up. Good there? Everything's kind of coming together here. Okay? All right. Okay, I'm just going to tell you this one. Correct answer is only B. Okay? I don't care after the car is splashed down in the water. I don't care about that. That's not projectile motion. I'm looking at how fast is it going right as it impacts the water. Okay, it's moving. It's not 0. This is the whole, remember the whole question, like if I dropped a bowling ball on your foot, would it hurt? Because, why? Because it's moving when it hits your foot. Okay? So, example problem, and then we'll be done. So a ball is thrown at 6 meters a second horizontally from a 10-meter tall tower. How far away from the base of the tower will it hit the ground? Okay. So I got a tower that's 10 meters tall. I throw it at 6 meters a second. I want to know, it's going to do that. I want to know how far away is it going to be. Here's my initial position. Here's my final position. Okay. So there's kind of the picture of this scenario. Now, when we go to set up our variables, this is the important part. You are going to, because horizontal motion is independent of vertical, we're going to separate out our variables into how is it moving horizontally and how is it moving vertically, because they're independent of each other. Okay. So start telling me what things I know and which side should they go in.
The vertical initial velocity is 0.
It's true. I'm going to hold off on that one. That is a very good yes. I'm going to go more at the ones that are given first. What else? What else do I know? Okay. In which direction? Vertical. What is the acceleration in the vertical direction? Acceleration in the vertical direction. You see why I'm doing a little subscript y here? Okay. What else do I know? What do I do with the 6 meters a second? Okay. That's going in the horizontal direction. So it is my initial horizontal direction. 6 meters a second. Okay. What else do I know? Nora. Okay. Is that vertical or horizontal? Vertical. Okay. Watch this. Instead of writing a delta x, I'm going to write it as a delta y. Horizontal, vertical. All right with that? And here's where a lot of people mess up. As a negative 10 meters a second. All right. Carolyn, what was? Okay. This right here is where, if you're going to miss the problem, this is where you forget. Your initial vertical velocity. It didn't say it in here, it didn't specify, but it did say it was thrown horizontally. It's thrown horizontally, your initial vertical velocity is equal to 0. Does that make sense? That right there. If you're going to miss the problem, that's because you forgot that. Okay. All right. And what are we looking for? What variable are we looking for? Trying to solve. Go ahead and tell your neighbor. Okay. Good. Now, the reason why we put this in the chart, we cannot have variables on here go over here like combine in one equation. Okay, we're going to keep them separate. They're independent of each other. Okay. Now, how would we describe the motion in the horizontal direction? How is it moving horizontally? How would you describe how it's moving? Constant what? Tell your neighbor. Constant what in the horizontal direction? Constant velocity or constant acceleration? Horizontally, it's moving constant velocity. There are no forces acting in the horizontal direction. Okay, so you could do this. So the final horizontal velocity would be what? 6 meters a second. And the acceleration acceleration is equal to what? 0. And we're looking for our horizontal displacement. And you could go, all right, don't write this. Just watch me on this one. You're like, sweet, I got that, and that. Boom. Yeah. Kinematic equations, rocking it out. 36 equals 36 plus 2 times 0 times delta x. 36 minus 36. You end up getting 0 equals 0. It's a true statement, not helpful. Okay? Can't go that route. That doesn't help me. Okay? So I'm like, ooh, I don't know what else to do. It'd be really nice if I had time, right? Then I could use my other equations. Does that make sense? Like kinematic equation wise, like another variable. I need another variable. Okay? Time is a special case. It's special because it doesn't fall in the horizontal or the vertical. It's just time. It doesn't have a direction. Okay? So could I figure out time from the vertical side? Is that a possibility? We've got acceleration, displacement, initial velocity, looking for time. Yeah, I got 4. I'm looking, hey, this is not bad, not bad. So looking through my kinematic equations, I'm going to choose this one. Okay, but I'm going to modify that and say in the y direction, in the y direction, in the y direction. So I just made that a delta y instead of a delta x. I didn't really change the equation. I'm just making it specific for the vertical. You okay with that? And then I can stick this in 10. Negative 10 meters is equal to 0 plus 1/2 negative 9.8 meters per second squared times delta t squared. Divide that and square root it. 1.43 seconds. Actually, I'm going to be a better teacher than that. Let's do this. 10 divided by 4.9. And negatives cancel out. So 2.04 equals t squared. Take the square root of both sides. Oops, I know what that is. It's 1.43. Plus or minus, we're going to choose the plus because time can't be negative. Okay. What can I do with that? So I've got this is how long it was in the air vertically, but that's also how long it was in the air horizontally. Okay, so I could use a bunch of different equations. My personal favorite, if we know this is constant velocity, we know the velocity is equal to displacement over time. You could use a bunch of different ones if you wanted to. This is my go-to. Okay? So horizontal velocity is equal to displacement over time. Put time into there. We got 6 meters a second is equal to displacement over 1.43 seconds. Multiply that. Gives me 8.57 meters, just meters. You look at that and go, is that realistic? Is that ridiculous? No? Sure, why not? Okay. Big picture. Draw your diagrams. Separate your variables into horizontal and vertical because they're independent of each other. You're usually going to try to find time. Time is the thing that can connect the horizontal and vertical motions. Okay? Got a worksheet due tomorrow.